electrostatics multiple choice. Explain as much as I can. So the first one, conducting sphere, radius, got a charge on it, and we want to know the field just outside the charge. Okay, so first, when we're looking at a metal sphere or an insulated sphere, if we're outside of the sphere, the electric field is just like a point charge. So it's just KQ over R squared. If we were inside a conducting sphere, the electric field would be 0. And if we are inside a uniform insulated sphere, well, that's the one that varies. It grows linearly, and then when you get to the edge, then it decays like a point charge. But remember, Gauss's law is used to find that particular charge, or that particular electric field inside. All right, so we got 2 charges here. Okay, we want an electric field of 0, and so where are we going to put this second charge? Oh, we want electric field 0 here. Okay, so we're going to be, we need to pull it because the positive is going to push it. And since it's going to be a -2, it's got to be further away, right? So it's a bigger charge, so it's got to be further away to have the same magnitude as the positive Q does, which is closer. The negative is going to pull it, and the positive is going to push it to the right, and those will then balance. Okay, well, if you have a positive here and a positive here, the electric field is actually 0 at A, because the left one's going to push it to the right, and the right one's going to push it to the left. And the electric field is a vector field, so they are going to cancel each other, and they're the same magnitude, so we want them the same distance. Okay, so when you put this rod in an electric field, the electric field is going to move the positive charge to the right. It's going to go with the field, and the negative charge is going to go against the field. So it's going to cause a net force to the left because this force is going to be bigger than this force. However, it also is going to cause a rotation because there is a torque on this thing. It is going to spin about this, and it is going to go counterclockwise. Okay. So they're that charge originally. Okay. And then they're allowed to touch. Okay. So when they touch, the charges are going to then get balanced. So they're going to flow back and forth. And so the whole charge on the system is a +1. So the +2 and the -1 make a +1. That +1 will then make it so there's a half charge on the left one and a half charge on the right one. And so then this is the original force right here on them both. K2Q over d squared. Well, now it's going to be K 1/2 Q times 1/2 Q over d squared. This thing is 8 times bigger than this thing, right? This is a 2 and this is a 1/4. So we've actually increased the force, decreased the force by 1/8. Okay. The charge on each sphere is doubled and d is halved. Okay. So it's like the doubling, tripling thing, right? If you double the Q's in the numerator, both of them, you create a factor of 4, but then the distance is squared and then you halved it. So halving the distance, squaring that makes a 4th, but that's a 1/4 in the denominator, which really makes it 16 times bigger. A charged particle traveling with velocity v in electric field E experiences a force F that must be parallel, right? The force is always parallel to the electric field, right? I mean, that is, they are the same, they are always in the same direction. That's the whole point of the electric field. It tells you the magnitude of the force that a Coulomb would experience, but it also tells you the direction of the force. Okay, so which of the converge is it 0 at the origin? Well, it's 0 at the origin in this guy, right? They're all symmetrically pointing down, 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 right? They all kind of cancel each other. In which electric field, in which configured electric field at P pointed at the midpoint between the 2 charges. And that's C. Okay, so in C, this one's going to pull left and up, and this one's going to pull right and up, and this one's just going to go up. So all of those guys end up balancing left and right, and they all go up. So So the electric field would go straight up. Here, they all completely balance and they cancel. And here they all balance x hat, but then there is a y hat component. All right, this one. Visually, this one's a little hard to imagine, but you are looking at the electric field as a function of x. So when x is 0, you're at the center of this ring. And so you know the E field is 0 when x is 0. And so like when you're right here and you move this way along, eventually you also know that if you get really far away, like way over here, that you also have an electric field of 0. So we know it's 0 at the beginning and 0 at the end. So honestly, this is your answer without doing anything else, because you know it has to be 0 and 0. The second thing is we also know that if you're just off a little bit, remember the y hat values are always going to cancel because there's always charges from the top of the ring and they're going to balance from charges from the bottom of the ring. But their x component are going to push this thing to the right. And if you're only a little bit to the right, well, then you only have a little bit of an electric field to the right. It's mostly vertical. But as you get to, like, let's say here, like that point right there, well, there is a significant amount of x hat from all the charges around that circle. But if you get too far, well, then it's going to get smaller. So you can see the x component electric field is going to build to a point, and then it's going to decay off until it is 0 eventually. Okay, from an electric field vector. From the vector, we know the direction and the magnitude, and that is the whole point of the electric field, right? An electric field is like 50 newtons per coulomb in the x direction. We know how strong the force would be on a charge at that point. But again, the electric charge at that point, that's completely meaningless when you're talking about an electric field. Electric field is coming from other charges. All right, they try to trick you on this one. They make it an electron. Just be careful. An electron's going to do opposite. We know the electric field is going straight up in this case. And so what is the direction of the force on an electron? Well, it's going to go to the bottom, right? Electrons are going to go down. They're going to go against electric fields. The electron's going to go towards the positive charge and away from negative charges. All right. All right, so these are conducting spheres way away from each other, right? There's no picture with this one. And one has a radius of r/2, and they have the same charge. And they're far apart, so they're not really influencing each other. So the electric field is just kq over r squared, and one of them is an r/2. So you square that and you get a factor of 4, right? The electric field, just imagine that they're point charges, right? You're basically twice as close to one as you are the other, so it's going to be 4 times stronger because the electric field is related to r squared. All right, 2 metal spheres. Okay, so now we're talking about this picture for 14. Okay, a negatively charged rubber rod is brought close to but does not make contact with sphere X. Okay, so the negative charges are going to come on this side of X when the negative is brought close. And then Y is brought close and they're allowed to touch. Okay, so when Y touches it, some of the negatives are going to be like, you know what, I don't even want to be on X anymore. I want to be as far away from the rubber rod as possible, so they're all going to go to Y. And then, okay, it's touched and it moved away. So then this Y is going to be negative. And then the rubber rod is moved away, and so then X is going to be left positive because you were allowed the net charge from net electrons to go to Y. You removed Y, so it's going to be negative chilling over here, and then X would be left net positive. All right, so now, okay, now we're looking at this picture for 15. I know that can be confusing at times. Okay. Oh, that's pretty much the same question, right? You're just polarizing this. You're just bringing negative close, and you're chucking the electrons over to number 2 because it's in contact, and that's just kind of where the question ends. So yes, number 2 would be negatively charged. Now, if you took if you left them in contact and you took the rod away, then the charges would balance again, and they'd both be back to neutral. All right, so we're looking at this picture here. What's the direction of the force on the test charge due to the other 2 charges? This one's going to push it down. This one's going to push it left. Thus, the resultant is down and left. So we got this guy. Again, it's always with respect to a positive charge. What's the magnitude on the force of the test charge due to only... If F is due to one of them. So if we have F down and we have F to the left, Well, the resultant is the Pythagorean theorem, so that's just f squared plus f squared, which of course is just square root of 2 times f, right? It's not going to be 2f, right? That's not how vectors add. These are definitely not that. All right. If the only force acting on an electron, again, is due to a uniform electric field, the electron moves with constant acceleration. Remember? Constant electric field, constant force, constant acceleration, right? That's basically just going back to F equals ma. Two charged particles. Okay, so we got two charges here. Which of the following shows the graph of the magnetic field along the x-axis from the origin to 6? Oh, okay. So the electric field, oh, the magnitude. So we don't care about whether it's negative or positive. We're just going to see what's happening to it. Okay, so electric field here is kind of small, and then it's going to get bigger and bigger and bigger as I get closer to that bad boy. But then when I'm inside of this, well, 2 is going to push me hard to the right, but 3 is going to push me a little bit to the left. So it's actually not as strong. Here, in this region here, they're both working together. In this region here, they're actually working against each other. And when you get to 3, it's actually 0, which makes sense that this point here is there. Then as you get closer here, closer to that guy from the left, it's going to grow. And then when you get over here, it has to be symmetrical to grow again. So this right here kind of makes sense. And you don't really care about the direction because they said the word magnitude. Which of the following describes the directional electric field at point P? Okay, so this Q is this small up and right, and this negative 4Q is going to be this bigger down. So you do have components in the x direction and in the y direction. Excuse me, negative y direction, right? It's going to effectively, those two would add together to be right and down. All right, we're almost done, right? We're done. Which of the labeled points on the x-axis is the electric field 0? Okay, so you can't be in the middle because you're going to be pulled and pushed and you're going to get thrown this way. You can't be, so if you're in over here, the Q pushes you to the right and the negative 4 pulls you to the right. So that's not going to work. If you're over here, the negative 4 is going to move you left and this plus 4 is going to move you to the right, but the left is always going to be stronger because you're closer to the bigger charge, which makes them double like stronger, right? Over here though, right, you can be closer to the smaller one and further away from the bigger one. This one will push you left, this one will pull you right, and they can cancel. And if you think about the position A, you're actually double the distance away from the 4Q as you are the Q. Doubling the distance makes it fourth, and it balances the fact that this charge is 4 times bigger. So then those forces cancel, or the electric fields cancel, right? So A makes sense. All right, last one. When a negative charge rod is brought near but does not touch, the leaves spring apart. Agree. So we bring this negative rod close to this thing. These negatives are going to spring apart because you've made the electrons want to go away from the negative rod, and they all go to the leaves of the electroscope, and then they're going to separate. Okay. Then the electroscope is touched with a finger, which allows the electrons to leave the leaves and go through you to the ground, which again leaves the electroscope back to being neutral. And then when you go away from this thing, then the charges are going to be positive because you've allowed the electrons to escape through you, through the ground. And then when you remove your finger, you don't give the electrons a path to get back on there. So since the electrons can't get back into the system, well, then you actually left it positive. Okay? So it's kind of like you are giving the electrons in the electroscope. First, you shove them down here, and then you give them a path to escape, and then you've left it net positive. Okay? So hopefully that gives you a good idea on how to look at electrostatics, E fields, and forces.